So, good afternoon, class. Um, have you guys touched on feedback amplifiers in class? Okay, great. So basically, feedback amplifiers are circuits. Under this particular topic, there's different topologies that we basically look at, right? So there's a total of 4 topologies, right? These are the 4 topologies that are present. So it depends on the configuration. So you can see the first configuration is series shunt. Like there's four topologies altogether. One is series shunt, shunt series, and shunt. So basically, how I remember this um, is that when you measure the voltage, you measure across something, isn't it? Or you measure voltage in parallel, right? And when you are measuring current, you measure it in series, isn't it? So this is towards the last part, right? Towards the ending part. So whenever you're looking at the end part, you can see in this particular case, the feedback amplifier is in parallel with this output, isn't it? So what happens is, like I said, you measure voltage in parallel, isn't it? So what happens if the feedback amplifier is in parallel to your output will be will be voltage. So if your feedback amplifier is in series with your output, it will be current. So it pretty much is similar to the way you measure the current and voltage, right? So that is how you can reflect. However, for your input, it will be the other way around. So if for your input side, if your input is in series, so what happens is it is opposite of this particular theory. So when you are measuring the voltage in parallel, so in the input side, it will be opposite. So if the feedback amplifier is actually in series with your input, it is going to be voltage sampling, right? So it will be basically sampling voltage. And if if your feedback amplifier is in parallel with your in parallel with your input, you will be basically sampling current, right? In that particular case. So in this particular case, you can see for the first circuit, you can see that your input is actually is in series while your output is in parallel with respect to the feedback. So what happens is if your input is in series, so you'll be basically sampling voltage at the, you'll be basically mixing voltage. And when your output is in parallel with the feedback amplifier, you will be basically sampling voltage. So in this particular case, it is voltage, right? So you'll be mixing voltage and you'll be sampling voltage. So over here, you can see that your feedback amplifier is actually in parallel to your input, and your feedback amplifier is in series with your output. So for your output, remember, if it's in series, it is going to be current, right? So your output is in series with respective, the feedback amplifier is actually in series with respect to the resistive load, right? So what happens is you'll be basically sampling current in this particular case, right? And since it is going to be opposite for your input, so in this particular case it was series for your output, so you are sampling current, you're sampling current. For your input, it will be the other way around. So if it's in parallel with this system, it is going to be current mixing, right? So you can see the feedback amplifier is actually in parallel in this particular case. So that is why it is going to be current mixing and current sampling. Okay. So using that same theory, just remember the output part, right? So for the output, if your feedback amplifier is actually in series, you are going to be basically your output will be current. Or if your output if the feedback amplifier is in parallel to your output, it's going to be voltage. For your input, it is the other way around, right? It's opposite. So you can see over here, your input is in series, your output is also in series. So it's a series. So your output is going to be current, right? And your input is going to be voltage. So voltage mixing and current sampling for this particular case. For this particular case, your output and your input are both in parallel with respect to your feedback network. So what happens is your input is in parallel. So what happens is you're basically mixing current and your output is in parallel with your load resistance over here. So you'll be sampling voltage. So the topology, each topology is explained over here. So a series shunt is basically going to be voltage mixing and voltage sampling. A shunt series is going to be basically current mixing and current sampling, while C, this particular diagram over here, is going to be voltage mixing and current sampling. That is basically series topology. And D, current mixing voltage, D is basically current mixing and voltage sampling, since it's a shunt. So that's one easy way to remember, right? For the easiest way to remember is you check whether your feedback, just with respect to your output, right? Just forget about the input. Just remember your output. Just by remembering that the voltage is actually measured in parallel, while current is actually measured in series, isn't it? So keeping that theory in mind, right? If your feedback network is actually in series with the output, right? If your feedback network is actually is in series with your output, you're basically going to be sampling current. And if it's in parallel, it is going to be voltage sampling. Your input is going to be the other way around. So your output was in series, it is voltage. So in parallel, it is going to be voltage. So your input is going to be the other way around. So it is in series, it is going to be voltage. So is that clear how you sample this? That's one way of remembering it. Okay. Is that fine?
Yes, sir.
Okay. Yeah. Okay. So that's regarding that. And then regarding your input input feedback resistance and output feedback resistance. So what happens is when you have two resistance in series, you add up the resistance. So basically your resistance grows, isn't it? And when you have two resistance in parallel, what happens is that resistance sort of decreases. For instance, if you have two 2K resistors in series, it is going to add up, isn't it? So it will become 4K, right? So in series, it adds up. But in contrary, if you have two 2K resistors in parallel, what happens is the total resistance of those parallel resistors will be halved, isn't it? So the total resistance of two 2K resistors in parallel is going to be 1K. Okay, so basically, just remember in series, your resistance increases. In parallel or in shunt, right? Parallel is also known as shunt. So whenever you have parallel or shunt, your resistance is going to be basically going to decrease. So over here, you can see for your input part, right? Series shunt. So your input is in series. So what happens is, in order to find the input resistance, you just basically have the input resistance multiplied by the feedback factor. Your output is shunt, so resistance divided by the feedback factor. Same goes for this series. So what happens is series resistance increases, so you just multiply the feedback factor with Ri, right? Your output again is in series, so you just multiply by the feedback factor with the output resistance. Same goes for your shunt. In shunt, remember I said the resistance decreases, so you just divide. So your Ri divided by feedback factor. Shunt, your output is again shunt, so R naught divided by the feedback factor, right? So that those are just some of the simple tricks to remember this, right? So this week's tutorial is basically 3 questions that were given for your tutorial, right? So question number 1, it says a current amplifier with a short circuit current gain of 100 ampere per ampere, an input resistance of 1K and an output resistance of 10K is connected in negative feedback. Negative feedback loop employing the shunt series topology, right? The feedback network proves a gain equal to 0.1 ampere per ampere. Estimate the current gain, the input resistance and the output resistance of the amplifier, right? So it's a short circuit current gain. So basically what this means is that your open loop gain is basically 100 ampere per ampere. And the feedback network proves a gain of 0.1 ampere per ampere. So in this particular case, your beta value, right? Your beta value is going to be 0.1 ampere per ampere, while your open loop gain, or A, is basically going to be 100 ampere per ampere. The other things we need to remember is that our input resistance is 1K and our output resistance is 10K. So we have to estimate the current gain, the total overall feedback current gain, and the input resistance and the output resistance of the feedback amplifier. So, like I said, your first thing is to calculate the feedback factor, right? Feedback factor is basically part of both, what do you say? It's part of both the, wait, let me go over here. Yeah, you can see that the feedback factor is part of both closed loop gain, and the input is also part of your input resistance and your output resistance, okay? 1 plus A, 1 plus A beta, right? So 1 plus A beta is part of your closed loop gain, is part of your input resistance and your output resistance as well for all the cases. So first thing, you can just start off with the feedback factor. So in this particular case, the feedback factor is basically given by 1 plus A beta. So like I said, your A value is 100, open loop gain is 100, and your beta value, or the feedback gain, is basically equal to 0.1. So the feedback factor is basically 1 plus A times beta. So this is what you get, 1 plus 100 into 100 times 0.1. That is going to be basically equivalent to 11. Now to find our output resistance, output feedback resistance, so output feedback resistance, let's go back to the question. It says it is using its shunt series topology. So shunt is your input, series is your output. So in order to find your output resistance, you have to multiply the feedback factor to your output resistance, and your input is shunt, right? So what happens is you divide the input resistance by the feedback factor. So going back over here, right, you can see the same thing, shunt series over here in the class notes as well. For shunt series, your input resistance, since your input is shunt, it is going to be divided by the feedback factor. Your input resistance is basically going to be divided by the feedback factor. For your series, your output is series, so it is going to be multiplied by the feedback factor, okay? So going back to the solution, so in order to find our output resistance, we are going to multiply, or is basically given by output resistance multiplied by 1 plus alpha times beta. So our output resistance in this particular case is given by, in the question, sorry, is our output resistance is 10K and our input resistance is 1K. So in this particular case, our output resistance is going to be 10, and 1 plus A times beta is going to be equivalent to 11. So R naught value is equivalent to 10, right? So 10 times 11 is basically going to give us 110 kilo ohms, right? Because this is 10 kilo, okay? This is 10 kilo. So our output resistance for the feedback network is going to be 110 kilo ohms. For our input feedback resistance is going to be given by input resistance divided by 1 plus A beta, right? Or AB is equal to our RI is basically equivalent to, or input resistance is basically equivalent to 1K, that is given in the question, right? So 1K divided by 1 plus AB. 1 plus AB is basically equivalent to 11. So 1K divided by 11 is going to give you 90.9 ohms. Okay. Then current gain. So current gain in this particular case is going to be AF. You can see in this particular summary table, the closed loop gain is basically given by A upon 1 plus A beta, right? So for all the cases, it is going to be A upon 1 plus A beta, right? So the closed loop current gain is basically equivalent to, or the feedback gain is basically equivalent to open loop gain divided by 1 plus A naught beta, or AB, right? So 1 plus AB is basically 11, and A naught value is basically equivalent to 100. So 100 divided by 11 is going to give you 9.09 ampere per ampere. Don't forget the unit over here, okay? Since the system is a shunt series, so you are basically mixing current and sampling current. So your input and output are both current. So your gain will be also ampere per ampere, okay? These are the units for current measurement. So don't forget about the current measurements. I mean the units of this particular variable. Okay, the feedback gain. Question number 2. So everyone is clear with question number 1? Okay, moving on to question number 2. Right, question number 2 says a shunt series feedback amplifier shown in figure operates with a supply current equivalent to 100 microamps, a feedback current of 90 microamps, and an output current of 10 milliamps. What is the open loop gain, A naught, and what is the feedback factor? Approximate and exact values. So basically, we first have to calculate our open loop gain. So our open loop gain. So our open loop gain is basically the current input to the open loop circuit and the current output of this particular open loop circuit. So in this particular case, it will be I naught. The output of this particular the open loop gain is going to be I naught, and the input to this particular circuit is going to be IS minus IF. So whatever, I mean, after removing this IF value, the remaining current goes into this particular network over here, this highlighted network, isn't it? So going back to our solution over here, our I naught is basically equivalent, our open loop gain is basically equivalent to the output of this particular block, right? The output of this particular block, that is going to be I naught, definitely, right? Like I said, so it is I naught upon the input to this particular block is going to be, the input to this particular block is basically IS minus IF, okay? So our open loop gain is basically I naught divided by IS minus IF. The values are given in your question. So your I naught value is basically 100 milliamps divided by our supply current, that is 100 microamps, and our IF is 90 microamps. So subtracting those, I mean IS minus IF, if you do that, you'll be getting 10 microamps. So 100 milliamps divided by 10 microamps is going to give you your open loop gain, that is going to be equivalent to 1000. Okay. Second part of this particular question is part 2 of this particular question. We have to find the feedback factor. Remember, this is our open loop circuit, right? This gray part, which is the I mean, that is system A, right? And this blue highlighted one is the feedback system, right? Okay, the beta circuit that we say. So in this particular case, we have to calculate the feedback factor of beta, right? So beta is basically, if you need to calculate the exact beta output, it is going to be equivalent to IF divided by I naught. Remember, feedback is going to be the other way around. Like feedback is always from this side, right? It goes from this side becomes your input, and this side is your input. So your input to this particular beta circuit is basically your I naught, okay? And the output of this particular circuit is your IF. So your beta part is going to be basically your output upon input. So your output is IF divided by your input, that is going to be your I naught, okay? Your I naught is your input, and your output for this beta circuit is IF. So calculating your beta value, that is going to be the exact value. So beta value is basically equivalent to IF upon I naught. So your I naught value is 90 microamps. Divide by your output current, that is 10 milliamps. So your beta, right? Your beta value or the beta gain for that particular of this particular blue highlighted circuit is basically equivalent to 0.009 to be exact, right? So this is the exact value for beta. Then we need to also find the approximate value of beta. So basically our feedback gain is equivalent to A upon 1 plus AB, right? So in case A times B is much greater than 1, right? If A times B is much greater than 1, so what happens is this particular equation is going to be, the denominator is basically going to be dominated by the A times B value, isn't it? So in that particular case, this particular equation simplifies or approximate, it becomes an approximate of alpha, A upon A times B, right? So you can simplify this into this, right? Remembering if A times B is much greater than 1. Then we can further simplify this, right? This A and this A cancels off. So the approximate feedback gain becomes approximately equivalent to 1 upon beta. Okay. So this is how you derive the approximate formula for IEF, right? So based on this, right? Based on this, you can see, you can make, if IEF is approximately equal to 1 upon beta. So basically a beta is going to be approximately equal to 1 upon IEF, isn't it? Right? So in that particular case, our beta is basically approximately equal to 1 upon AF. So in order to approximate our beta, we have to find our feedback gain, isn't it? So to calculate our feedback gain, right? So our feedback gain is basically given by I naught divided by IS, right? Your input divided by your output. I'm sorry, your output divided by your input. So IF value is basically given by output divided by your input. That is basically equivalent to your output value given is 10 milliamps. Your input or the supply current is basically equivalent to 100 microamps. So substituting those two values is going to give us our AF value, that is going to be 100 to be exact, right? So our feedback gain is basically 100 to be exact. All right. So once we have our AF value, we can approximate our beta value. Remember, our beta is approximately, making beta the subject of the formula. Beta is approximately equivalent to 1 upon AF. Okay. So once we have our exact AF value, we can substitute it into this particular formula to find our approximate beta value. That is basically equivalent to 1 upon AF. So AF value is 100. So 1 upon 100 is basically equivalent to 0.01 approximately. So you can see the approximate value of beta is also slightly equivalent to this particular value, right? If you take two decimal places of this particular value, the exact value and the approximate values will match. And in case if you want to approximate the feedback gain, so feedback gain is basically approximately equivalent to 1 upon beta. So we need to use the exact value of beta. So in that particular case, our approximate feedback gain will be equivalent to 1 upon beta. So the exact value of beta is 0.009, right? So in that particular case, 1 upon 0.009 is going to be equivalent to 111, right? So you can see that the approximate feedback gain and the exact feedback gain differs. And there is a huge difference. So 11 is the difference between those two. So you cannot use that for approximating the feedback gains. So in this particular case, the question asked us to find the exact value for beta. So that is what we have calculated. And we needed to find the approximate value of beta that is what we have calculated over here. This is just an extra part, right? This was not needed, but still it has been presented. So is that okay? So anyone has any questions regarding this one? Question number 2. Anyone has any questions? Okay, so I believe there's no questions. So we move on to the third question. Again, in the third question, it says a circuit shown below identify okay, a circuit shown below identify type of feedback at the output and input, right? So there's an error over here. So it should be identify. A circuit shown below identify the type of feedback at the output and the input. Find the feedback factor, right? And closed loop gain AF. Also find the approximate closed loop gain. So we have to find the approximate closed loop gain, right? We have to find the approximate closed loop gain. We have to give the solution for our closed loop gain and our beta factor as well. So first thing first, we have to identify the topology of this particular circuit, right? So just by observing, you can see that this is your feedback network, right? This is your feedback network. Okay, this is your feedback network. So first thing, you check whether your supply voltage is in series or in parallel to your feedback network. So in this particular case, it is going to be a series network, isn't it? Your supply voltage or your feedback system is in series with your input, right? So your input is basically series, right? Input is basically series. So I'm just going to represent it by S, right? And your output is going to be in parallel, right? Isn't it? Your feedback network with respect to your RL network, it is in parallel to each other, okay? Or you can say your feedback network is in parallel to your output. Your output is measured across RL, isn't it? So it is in parallel to your output. So I'm going to represent that by P. So it is going to be a series parallel network. Or we say it is going to be a series shunt, right? A series shunt. Another way, another name, I mean, usually parallel is said to be shunt, right? So it is a series parallel network, or it is a series shunt network. So when we have a series shunt network, when your input is, when your output is in parallel, right? When your output is, or your feedback network is in parallel with your output, but what are we sampling? We are sampling voltage. And for your input, it is the other way around, right? If we are measuring voltage in parallel, for your input, it is going to be the other way around. So if a system or your feedback network is in series with the input voltage or the current source, whatever source we have, it is going to be voltage. So basically we are mixing voltage and we are sampling voltage in this particular case. So the network type for this particular circuit is series parallel setup or series shunt network, right? So we are basically sampling and mixing voltage in this particular case. So we have to find the beta factor and the closed loop gain approximate and the exact feedback gain, right? So like I said, we are sampling output voltage and we are also comparing voltage at the input, right? Or we are basically mixing voltage and we are sampling voltage, right? Like I showed you into that in this particular second over here, in this particular question over here, right? So next is to actually uh, um, like I said, okay, yeah, so this is just a representation of this particular circuit over here, right? You can represent the same circuit, right? Like this highlighted circuit is beta and this particular op-amp is A, right? This bottom part is beta. And we can simplify this as a block diagram and we can draw it as this particular block diagram over here, right? So in this particular case, you can see your feedback network with respect to your load resistance is in parallel, right? Or your output is in parallel to your beta network. And with respect to your series, with respect to your supply voltage, it is in series, right? Okay. So once we have identified the topology, that is series shunt, in this particular case, we have to identify our closed loop, our feedback factor and our feedback factor and our closed loop gain, right? So that is AF and the approximate closed loop gain. So in order to find our beta, what you can do is so in this particular case, our beta network is going to be having the input to this beta network is going to be V out, right? The input to this beta network is V out, and your output of this particular beta network is VF. So V out, I mean VF upon V naught is basically equivalent to your beta, right? VF, sorry, VF upon V out just by observing is going to be equivalent to your beta. So our beta value, right? Our beta value, if you see this, check this particular network over here, right? You can see the output of this beta network. So this is our beta network. So the output of this is going to be given by, since the input to this particular network is a voltage, your output is also a voltage. What you can do is you can utilize a current division, isn't it? So using, I mean, sorry, a voltage division in this particular case. So using the voltage division rule, the voltage at this particular node, at this particular point is basically given by R2 upon R1 plus R2, isn't it? So voltage at this particular node, that is the same voltage that flows into this particular branch, is basically equivalent to R2 upon R1 plus R2, right? So that is what we have, and that particular voltage then goes through a gain block, right? That is K. So K multiplied by R2 upon R1 plus R2 is our beta value. Is that fine? This is how we get our beta value, because just by observing the input is voltage and output is voltage, we can see these two resistors are in series. So we can basically, and the voltage is basically drawn from this particular node. So we can use voltage division, right? In this particular case to find our voltage at this particular point. Let's say X. So voltage at point X is basically given by the voltage division, that is R2 upon R1 plus R2. And then that voltage is multiplied by the gain, that is K, right? So that is our beta factor. Is that fine? So beta is basically given by K times R2 upon R1 plus R2. Okay, this R2 upon R1 plus R2 is our voltage division at this particular point. Is that fine? Okay, so then this voltage goes through the K block. So there is the K, right? This is the indication that the voltage at this particular point is then amplified by vector K. So multiplying by K. So that is how we get our beta. Our VF upon V out is basically equivalent to beta. Beta is basically equivalent to K times R2 upon R1 plus R2. Next is to find the approximate, the approximate and the exact feedback gains. So like we did, the approximate feedback gain is basically equivalent to 1 upon beta. So once we have our beta value, right? Once we have our beta value, we can find our approximate gain, feedback gain, that is 1 upon beta. So 1 upon beta, so directly substituting these values in place of beta is going to give us R1 plus R2 upon K times R2. That is also equivalent to 1 upon K into 1 plus R1 upon R2. So this is the approximate feedback gain. Then we also have to find the exact feedback gain. So exact feedback gain is basically given by A upon 1 plus A times B, which is equal to A value remains as it is because we cannot calculate our A value, that is open loop gain, that we have to see what is the open loop gain for the op-amp, right? So we are going to basically represent the open loop gain by A. So A upon 1 plus A into the beta value that we have calculated. So this is the exact feedback gain, right? So you just leave your answer as it is because we are not given the values. So we just leave it like that. So is that clear with this week's tutorial? So since we have, we required to calculate the beta value, the AF the feedback gain, the exact feedback gain, and the approximate feedback gain, which we have done over here, the beta value, the approximate feedback gain, and the exact feedback gain. So anyone has any queries or any questions? So anyone has any queries or any questions regarding this week's tutorial? Okay, so everyone is good. So with that, we have come to a conclusion of this week's tutorial. So anyone has any other queries apart from this? Any other issue that you have in this unit that you want to discuss with me right now? We have another 5 minutes. Okay, so I'll give you a couple, one or 2 minutes because we have 5 minutes left before this session closes. Regarding lab 6, okay, yeah, sure, Anika. What is the problem? Yes, Anika, what is the problem? What is the query that you want to discuss? You can, it's totally up to you whether you want to combine figure 1 and figure. Oh, yeah. You have to, in place of G, you have to replace that with that particular part. You have to combine the circuits, right? The G is actually represented by the other circuit, and then you have to replace it into the main circuit. So it is more like a key, right? So that's how you read it in engineering drawing. So a block is basically, you know, what we have done over here, like the beta block, this whole beta block is represented by this small block beta. So in place of beta, we are going to place this particular block over here in order for the actual system to work. Likewise, for your lab as well, the G, the op-amp G is actually represented by one of the figures, right? That is made by an extended op-amp circuit. So you have to combine that in place of that. Okay. Okay. Set. So with this, we'll conclude this week's session, this week's tutorial, right? If you have any other queries, you can. So when increasing the frequency, the graph starts to significantly from regions. So yeah, just put the result, whatever results you have, right? Don't worry about the results. There will be some up and down. I mean, you won't be getting an exact shape like the one I showed you. There'll be some offsets, but as long as you get the exact, like, no, just get a overview of that image, right? Remember, it's going to be something like this. Wait, the graphs should give you a result of something like this. Okay. So as long as you have this sort of picture, or you have something like this that you can make out from, that is fine. There will be some errors up and down. Okay. Okay, it moves from the negative portion to positive portion. Okay, can you just message me or show me what exactly is your issue? Like, no, you can directly message me on Viber. Since this session is about to conclude, you can directly message in the group, okay? And we can, I'll drop a I'll answer your queries in that. All right. So with this, we'll conclude this week's tutorial session. Right. If you have any other queries, you can drop me a Viber message, or you can directly drop the message in the Viber group as well. If you find it will be helpful for the others as well. Okay. So have a nice weekend and see you next week.